Hello all of you. So in the last lecture we have discussed the idea of binodals and spinodals, and today we will discuss how can we use the Helmholtz free energy density to also get the osmotic pressure and chemical potential, and how osmotic pressure and chemical potential are also a measure of the driving force for mixing and phase separation. Let us first start with the osmotic pressure. The general picture in which we use the word osmotic pressure refers to an idea of the osmosis process, where we assume that there is a membrane that is permeable only to the solvent, and we look at the migration of solute and solvent in that particular problem. But that idea itself is more general. There need not be a membrane. Materials exert an osmotic pressure by itself, right? So, we will start with the idea of a membrane, but keep in mind that this membrane is just an hypothetical construct. In reality, what we are discussing is that it's a property of the material itself. It is a membrane doesn't have to be physically be there present for this pressure to exert. So, the picture is something like this. So, let us say if I start with a solution that contains both solute and solvent, which has a volume fraction phi for the solute, and on the other side of membrane, let us say we have the pure solvent, or we can say phi is equal to 0, and then we have a semi permeable membrane. And I re-emphasize that it is just a hypothetical kind of a construct. The idea is applicable whenever we have a solution and solvent. The membrane does not have to be physically present there. So, in this particular scenario, where we also allow the movement of the membrane to the left and right, in general we can say that the solution may occupy some volume V, and in total we have some V tot volume. Similarly, we have N tot molecules, which is Np plus Ns, and just like what we have been doing, we are working for the situation where Np, Ns, temperature and pressure are controlled, and therefore, we are interested in the Gibbs free energy for this particular system, and that is how we have been developing the idea of Helmholtz free energy density and all that. We always start from the Gibbs free energy, because when we have this thing constant, then the applicable energy function is the Gibbs free energy. So, for this particular system, what we can say is that the movement of this membrane will be in some sense driven by what is the movement of a solute, of the solvent in this particular case, because solute anyway cannot move through the membrane, right. So, if for example, the solvent wants to come here, since the liquid is assumed to be incompressible, the movement of the solvent must be accompanied by the movement of the membrane to the right, or we can say that the V increases as solvent comes in solution. So, in general, if I start this particular system, the solvent will have a tendency to pass through the membrane to the solution, and whenever that happens, there is a change in the volume of the solution, right. So, now if I want to stop that from happening, what I have to do is I have to apply some pressure, let me give it a name pi, to keep the membrane at a fixed location, right. So, if I want to keep volume fixed for the solution, we have to apply an external pressure on the solvent side, so that it compensates the tendency of the solvent to move, because as solvent was moving, the barrier was, or the membrane was coming to the right. So, we apply a counteracting force to stop that from happening. So, what this also means is that in some sense, by the idea of force balance, is that the solution itself is exerting a pressure, right. So, if I look at the force balance for the membrane, since we have to apply an osmotic pressure pi, I haven't given the name, but I will call that osmotic pressure. If I have to apply a pressure pi from solvent side, then it means that the solution is exerting the pressure pi from its side, right. So, therefore, we can say that there is some osmotic pressure of solution, and as you may imagine, this should be a function of phi, because let us say for example, when phi is very high, in that case the amount of solvent in solution side is less, and then we have pure solvent on the other side. So, you have a large concentration gradient, so as to speak, to begin with. When phi decreases as volume increases, that concentration gradient becomes smaller. So, that should result in a lower osmotic pressure or a lower requirement of pressure to keep the membrane at a fixed volume, right. So, this must be a function of the volume fraction, and this in some sense then is what characterizes the mixing behavior for this particular problem. So, let us say for example, if the solute likes the solvent, or if solute wants to mix in the solvent, then it will tend to increase its volume, because only then the solvent can come from the other side of the membrane, right. So, therefore, whenever we have a case where we tend to favor mixing, the volume has a tendency to increase, and therefore, the pressure is large. On the other hand, if there is less tendency of mixing, what this means is we have to apply lesser magnitude of pressure to keep the membrane intact, because anyway the tendency of solvent to migrate is less. So, the higher value of osmotic pressure implies a higher tendency of mixing, or we can say that pi is a driving force of mixing. Just to think of like an analogous situation where there is no membrane, we can imagine, let us say for example, an smoke start coming from one side of this room. The smoke has a tendency to fill the entire room, because smoke wants to be dissolved in the air in the entire room. Smoke does not have a tendency to phase separate, smoke has a tendency to mix. So, when this process begins, what we can say that smoke brings along with it some osmotic pressure, and it is that osmotic pressure that is driving the movement of the smoke. So, the volume of the smoke is increasing until we have a scenario where smoke fills the entire room. While that is happening, of course, the volume fraction of solute particles in smoke is decreasing. So, in this problem, the phi will decrease as the volume increases, right. So, that is the case when we have a tendency to mix. If on the other hand, if we did not have a tendency to mix, in that case, that osmotic pressure will be very small. So, in that case, whatever substance we have will remain as it is, or will undergo small changes in volume, right. So, therefore, pi pretty much becomes the driving force of mixing, but we have earlier established that I can characterize mixing with the function f, that is the Helmholtz free energy density. So, if that is possible, then it also means that this pi has to be a function of that small f. So, let us see how that happens. So, if you think about it, the pi dV with a minus sign, because the volume change that is happening is against the pressure that is being applied on the system, or if we think about work done by the system, it is going to be pi dV. Work done by the system, work done on the system is going to be minus pi dV, right? And this must be then equal to the change in the total free energy of the system, right? So, the work done needs to go into changing of the energy of the system. So, we can think in terms of the first law of thermodynamics, where I said that change in U is given as change in Q plus change in W. By the way, we typically represent that as du, since U is a state function, and these are delta Q and delta W because these are path functions. So, I said this is equal to TdS, and the second term we said is equal to minus pi dV. So, if I move this on the other side, you have du minus TdS is equal to minus pi dV, and this at constant temperature we can say is du minus Ts, and that is equal to my Helmholtz free energy, right. So, change in Helmholtz free energy is therefore equal to the work done on the system, and therefore, we can define pi as minus dou f dot by dou v, and that is happening at constant value of the number of molecules, the temperature and the pressure of the system, right. So, in this case pressure is if you think about it, is inconsequential, because we are assuming both pressure and volume to be related, because the system is incompressible. So, essentially temperature is the one that is more important, so as to speak. So, now the free energy in the total will be equal to free energy of the solution plus free energy of the solvent, and that we can write in terms of the free energy densities as V multiplied with f of V plus V tot minus V multiplied with f of 0, because on the solvent side the volume fraction of solute is 0, it is pure solvent, it is a pure solvent. So, now you should keep in mind that this phi is related to volume, Np and Vp are fixed. We are assuming constant Vp because system is incompressible, and Np is also fixed because we have kept that fixed in the partial derivative. So, therefore, I can write the dou f tot by dou v as something like f of phi plus v f prime phi dou phi by dou v, and then in the second term you will have minus f of 0. Now, let us find what is dou phi by dou v. So, dou phi by dou v is minus Np Vp by V square, and V again I can represent as Np Vp by phi square, and therefore, we can say dou phi by dou v is minus phi square divided by NP Vp. So, if I put that thing in here, what we then have is my pi as minus f dou f dot by dou v, that is minus of this quantity that I had, and then finally we had minus f of 0. So, if I look at this quantity, we can notice that NP Vp by capital V is still phi. So, one of the phi will cancel, and so we can write this as minus phi f prime phi, and therefore, I can write my pi as phi f prime phi minus f of phi plus f of 0. So, this is the expression of the osmotic pressure, and I showed you it is a function of f, right. So, this was expected because pi is a driving force of mixing, and we already said if I know a small f, I can characterize mixing. So, both has to be related. Now, let us look at the chemical potential. So, by definition, the chemical potential of the solute is given as dou G by dou Np at constant Ns pressure and temperature. Again, pressure is inconsequential here, and mu s is given as dou G by dou Ns Np pressure and temperature. Now, G is given as V multiplied with P plus F phi T, which we represented as f of phi, assuming that we are working at a constant temperature. So, then when I want to compute mu P, again we have to be a bit careful here, because as the Np is changing, the volume is also changing, right. So, we have to have, so the volume is equal to Np Vp plus Ns Vs. Whenever we are doing this math, the key thing is to see what is the variable that is being held fixed. In this case, Ns, P and T are fixed. We are not saying anything regarding the volume, right, and volume is clearly changing when Np is changing, because Vp is constant, Ns is constant and Vs is constant, right. So, we will put that form here. So, I can write my G as Np Vp plus Ns Vs F plus P, and now if I take that derivative, we still have to use the fact that phi will also change as volume will change, and this again we can write as Np Vp divided by Np Vp plus Ns Vs. So, now this quantity is going to be equal to, first of all we take derivative of the first term, that will give me Vp multiplied with second term will come as it is, and then I will take the derivative of the second term. So, pressure is being held fixed, but we have f prime phi dou phi by dou Np. So, let us first find what is dou phi by dou Np here. So, I said phi is equal to Np Vp divided by Np Vp plus Ns Vs. So, therefore, dou phi by dou Np will be equal to Np Vp plus Ns Vs, that is the denominator, multiplied with derivative of the numerator, that is Vp, minus the numerator multiplied with derivative of the denominator. So, this will cancel the first term right here, divided by the denominator squared, which will give me Ns Vs Vp divided by Np Vp plus Ns Vs whole square. So, if I put that thing in the expression that we had obtained earlier, what we are going to have is mu p is equal to Bp multiplied with P plus F phi, that was the first term right here, and the second term will be plus Np Vp plus Ns Vs F prime phi multiplied with dou phi by dou Np, and that is Ns Vs Vp plus Ns Vs whole square, using the term, that is second term right here. So, now again we have certain cancellations, and what we obtained is Vp multiplied with P plus F of phi plus Vp multiplied with F prime phi Ns Vs divided by Np Vp plus Ns Vs, and you can see that this term is actually equal to 1 minus phi. So, therefore, what we have is Vp multiplied with P plus F of phi plus 1 minus phi F prime phi, that is the expression of my mu p. So, now I can do the same exercise for the chemical potential of the solvent. That will be dou G by dou Ns at constant Np pressure and temperature. Again we start with G being equal to volume multiplied with P plus F of phi, that is Np Vp plus Ns Vs multiplied with P plus F of phi, and again when I took a derivative, what I find is mu s is equal to Vs multiplied with P plus F of phi plus Np Vp plus Ns Vs F prime phi dou phi by dou Ns, and since phi is equal to Np Vp by Np Vp plus Ns Vs, what we can say is that dou phi by dou Ns. So, in this case numerator will not have a derivative with respect to Ns, it will come as it is, and the denominator will be squared and we will have a negative sign. Multiplied with the derivative of the denominator, that is Vs, and therefore, if I put that thing back there, we will have mu s is equal to Vs multiplied with P plus f of phi plus NPVP plus NSVS f prime v, but now with a minus sign. Again we have cancellation, and what we had then is, sorry, there was a Vp appearing there. So, what we then have is Vs multiplied with P plus f phi minus phi multiplied with f prime of phi. So, the chemical potential can also be represented as a function of the f of phi. Now, let us pause for a moment and see that how chemical potential can also be a driving force. So, let us imagine that we have two phases that is not under equilibrium. So, clearly when that is present, then there is some exchange happening between the two phases, right. So, let us say one of the phases has some volume fraction phi 1 and the other phase has some volume fraction phi 2, and I want to know what is the direction of the transfer of the solute and solvent in this particular case, right. So, clearly the transfer is going to occur in the direction where the total Gibbs energy is minimized, but in terms of the chemical potential, it is driven by the gradient of the chemical potentials. For example, mu p in the first phase, if it happens to be more than the mu p in the second phase, you will have transfer of solute from phase 1 to phase 2. In other words, transfer happens in the direction of decrease of the chemical potential, or transfer happens from a higher chemical potentials to a lower chemical potential. Similarly, for solute, if mu s in the second phase happens to be more than the mu s in the first phase, that will be giving me the direction of the solvent transfer, right. So, in this case solvent will go in this way because I am still going from a high chemical potential of solvent to low chemical potential of solvent, because in second phase the chemical potential of solvent is more, right. So, ultimately we are interested in the gradients of these chemical potentials, because it is these gradients that dictate in which direction the transfer will take place, right. So, let us start with the expressions that we had obtained for mu p and mu s and find these gradients, right. So, let us start with the first one. So, I have found mu p is V p multiplied with P plus f phi plus 1 minus phi f prime of phi, that gives me dou mu p by dou phi is equal to V p multiplied with f prime phi plus, we will have 1 minus phi multiplied with f double prime phi minus f prime phi. So, we have some cancellation. So, dou mu p by dou phi is essentially V p multiplied with 1 minus phi multiplied with f double prime of phi. On the other hand, mu s we have obtained as Vs multiplied with P plus F phi minus phi F prime of phi as we had obtained previously. So, therefore, dou mu s by dou phi is going to be Vs multiplied with F prime phi minus phi F double prime phi minus F prime phi. So, again we have cancellation and we get minus Vs phi F double prime phi. Now, we look at the scenarios that we had obtained earlier. So, I said when F double prime is greater than 0, then we have a tendency of mixing. What does it translates to in terms of the dou mu p by dou phi and dou mu s by dou phi? What it means is that my dou mu p by dou phi, that is this particular term, it is also going to be positive because phi is a number between 0 to 1, Vp is a positive number. So, if F double prime is positive, then dou mu p by dou phi is also positive, and dou mu s by dou phi is going to be negative because we had a negative sign. So, this means that mu p is actually increasing as phi is increasing and mu s is decreasing as phi is increasing. So, now starting from this argument, let us say I want to consider a situation where I start with pure solvent and the solution. Solution had some phi and pure solvent has phi equal to 0. And let us say I put them together, there is no membrane in between them or something of that sort. So, in that case, I have just said that if F double prime is more than 0, this means that mu p is going to increase as phi increases, but mu s is going to decrease as phi increases, right. So, clearly in this particular case, if the solute moves from the solution to the pure solvent, then phi is decreasing, right. So, for solute movement, phi will decrease when we go from solution to the pure solvent phase, right, and only that will result in a lowering of chemical potential, because if the transfer is other way around, that will result in increase in the chemical potential, and I just said we want to go in the direction of decrease in the chemical potential, right. So, pretty much this tells me that solute has to go from solution to the pure solvent phase. However, for the solution, the chemical potential is decreasing as phi is increasing, right. So, we begin with phi equal to 0. So, when the solute comes into there, then the phi increases, and that is favored because chemical potential of solvent is decreasing, right. So, a motion of solute from the solution phase to the solvent phase is favored both by the chemical potential of solute, because that results in lowering of the chemical potential of solute, and it also favored by the chemical potential of solvent, because increase in phi results in lowering of the chemical potential of solvent, and therefore, we have a tendency of mixing. On the other hand, if F double prime is less than 0, in that case, what is going to happen, and let us say I again start with solution with some volume fraction phi, and a pure solvent, that is with phi equal to 0. In this case, we will have the opposite situation. So, mu p will decrease as phi increases, but mu s will increase as phi increases. In this case, the solute movement should be other way round, right? That means, if I start with pure solvent, there is no movement. Why is that? Because if I go in the opposite direction, that will result in a lowering of the phi, and the lowering of phi will give me an increase in the chemical potential, because chemical potential decreases as phi increases. So, if we have decrease in phi, that will give rise to increase in the chemical potential, and that will clearly not be favored, right. So, we cannot have the tendency for a solute to go from solution phase to the solvent phase. Similarly, the chemical potential of solvent also increases as phi increases. So, any solute transfer from solution to the solvent will result in increase in the chemical potential, right, and that is also not favored. So, therefore, the system will have a tendency to phase separate. So, the key point of the discussion that I wanted to emphasize is that the tendency of the mixing and phase separation can be described also in terms of osmotic pressure and chemical potential, but since they are related to the Helmholtz free energy density, or they can be written as a function of Helmholtz free energy density, we do not have to consider them independently. If one of them is telling me that mixing will happen, we should be confident that mixing is going to happen, right. So, the final point I wanted to make here is that although I have derived the expression of the osmotic pressure in terms of f of phi, and similarly the expression of chemical potential as a function of f of phi, it is not necessary that I first calculate f of phi and then calculate pi. It can be other way around. If I have the expression of pi, I can also calculate the expression of f of phi, and the same is true for the chemical potential. If I know chemical potential, I can use that to find the f of phi. Where it becomes important is because for many equation of states, it is more convenient to write the equation of state in terms of the osmotic pressure as opposed to the Helmholtz free energy density. So, in those cases, if we need to compute the Helmholtz free energy density, it is very much possible. So, if you just think of doing the opposite of what we are doing, so I can write my pi as phi dou f by dou phi minus f of phi plus f0, and if you look at these two terms, this I can write as something like minus phi square dou by dou phi of f by phi. Why? Because if I elaborate this, we will have minus phi square phi dou f by dou phi minus f of phi divided by phi square. So, there is, by the way, there is a plus sign here, and this cancels, and we have right. So, therefore, I can write phi square dou by dou phi f of f by phi is equal to pi. So, if I know the expression of pi, I can integrate this and find the expression of f. So, with that, I want to conclude the discussion here. In the coming classes, I will discuss how can we obtain this Helmholtz free energy density expression f of phi using the lattice model of solutions. Thank you.